So now is the time that you can ask us anything. So, well, you can also ask us anything during the garages, of course, but now's a time we can discuss together as a group and everyone can hear. Yeah, so sorry. Okay, so what's the general, also don't forget the feedback down here. This would be quite good for us to hear about.
Yeah, definitely. Like this is such a info dump. There's so much stuff here. So it's very hard to know what we should prioritize because at that point it's very important that we would know what our user base wants and what you want, because then we can make this course better for the next generation. Like what I mentioned earlier, like does everybody have to go through the same crucible? Hopefully not. Like hopefully people can, like the teaching methods what we are employing can improve, and hopefully like next people to have even better understanding of what
so
they need to do.
There's a good question there. Would you recommend some further tutorials with GPU calculations? I never had ran parallel calculations, but thing to try to use. So I guess what kind of tutorials? Like writing your own CUDA code or using GPUs on Slurm or using some existing library? So I'd say that most people these days doing at least the data science, machine learning kinds of things, use codes that already have GPU support enabled. In which case you look at the code and you see how does it say to use it, and then you adapt that and write an SBatch script to submit it to the cluster. If you're making a brand new code, like if let's say you were a physicist and you were doing some simulation and you thought that, okay, I can make my simulation go faster with a GPU, and you're writing it yourself. That's a whole other thing. And in fact, there's a workshop starting tomorrow that will talk more about this kind of thing. And maybe that's a good place to go. This workshop is not designed to talk about one particular programming framework, but sort of go over like what the landscape is and what tools would you be using.
Yeah, and also I would mention that there are various like for example, like if you just want to try like CUDA program or GPU using GPUs for your problems, like for example, like NVIDIA has this Rapids environment that uses like GPUs for running like Numpy things. So if you write stuff in Python using like Numpy, you can basically like change the import statement and it should run on the GPU. And like there are lots of these frameworks that make it like you need to do minimal changes to your code so that it runs on the GPU. These are, of course, the questions of is it worth the effort? Like I would say that in many cases not, unless your program is very heavy. But if you are interested in like GPU, like CUDA program itself, like CSC, for example, has a nice course on CUDA programming. I put a link to the answer.
Okay. Yeah. Yeah, today's stuff was definitely a bit like an info dump, wasn't it? I mean, so the GPU course starting tomorrow is full days and two full days just about the basics of the GPU landscape. And here we spent what, half an hour on it or something.
Full 20
So,
minutes.
Yeah.
Yeah.
Yeah, but like maybe I should have said this before, but I would reiterate that when it comes to Slurm, like how does Slurm think of these? It's like these few flags that you usually need to use. So like if you think about CPUs, just ask for CPUs. If you're using MPI, just ask for tasks. If you're using GPUs, just ask for a GPU. Like it's not rocket science. Like you just write your Slurm script and then you add these extra things. The question is that, like, how do you let your program know what it needs to do and that sort of thing? And they are then it gets complicated. Depends on a program.
Yeah. If I'm using Numpy for a large program in my personal laptop that doesn't have a proper GPU, would this make the processor run the program? What is this?
Like
So
I think it's
NumPy's
yeah, I think it's related to what I mentioned previously about like this rapids environment.
And also we should point out that things like NumPy, so NumPy is a Python library that uses a lot of other libraries written in C and Fortran for a lot of the things it does, especially like linear algebra and so on. So NumPy itself is capable of using multiple CPUs with the shared memory paradigm. So if you request multiple processors that way, your code can speed up. But it's not just magic anything NumPy. It's only if you're using the NumPy library functions, which are made in a way to do this.
I will quickly mention that I would recommend, like if you feel like it's such a big program that your like computer gets heated up or you can't use the browser while you can't do anything else while it's running, try to move that to the cluster. Like that, like you don't have to always jump to CPUs or GPUs. Of course, like if it's such a problem that you want it to run a lot faster and that sort of thing, then sure. But I would first step I would probably try it out, like just run the same program on the cluster, then it wouldn't bother me. Then I would try to speed it up or add more CPUs and that sort of things to make it run faster. But even that thing that it runs somewhere else and it doesn't bother my other work is a extra benefit already. Like you don't have to worry about it if it's running in the queue.
Yeah. So I see it says there's 57 people on the notes and 51 on the stream. If you're hearing this, you really need to go to the notes and fill out the feedback because that's the only thing that keeps us motivated here.
So
it's a good question. What are TPUs?
So yeah, they're basically Google's own GPUs. So Google has written these. Well, I don't know what is the exact architecture because it's probably hidden. But they have these TPUs, which are like tensor processing units, and they have them in like Google Colab and if you do like the Google Cloud like calculation service or what's it called, like they have the stuff there. They are basically like GPUs, so they calculate similar kinds of calculations. They don't have any graphical processing, so they're basically only like these accelerators. And they are usually like when you're running like let's say PyTorch or TensorFlow on them, you're basically using these compiled kernels that Google has created. Because eventually, like most of the deep learning stuff, it's just like these simple or certain calculations that are usually maybe optimized for the architecture. And then like PyTorch and TensorFlow, they decide which system to use based on either user suggestion or based on what is available in the system. So they are another way of doing it.
Okay, yeah.
Is the hardware like the same, the TPUs and the GPUs?
There's some like difference. So like this gets very technical. I don't want to maybe go there.
You can say no or yes.
It's like GPUs have different ratios of different kinds of calculating units. So like for example, like I would give an example that if you're running let's say physics code on a workstation where you have like a gaming card, Well, the gaming cards usually don't have like calculating units for calculating double precision numbers. And physics often uses double precision numbers because, like, if you don't know what double precision is, then don't worry about it. But basically, physics code usually want to have lots of precision because you can have like all kinds of problems if you don't have it. But if you're doing like if you're playing CS:GO or Fortnite or gaming, you don't care about that. So the machines themselves don't have these calculators. Like the gaming GPUs don't have these calculating units. But these more advanced machine GPUs, they have these calculator units. And these Google TPUs, they have these matrix multiplication, these tensor product units or tensor calculation units that can do multiple calculations at the same time. So it's the hardware is different because it's suited better for different kinds of calculations.
Okay. So yes.
Yeah.
Yeah.
Okay, so the gaming GPU is no use for my own calculations.
No, I
can
would
still
say
be.
that. Yeah.
It can still be quicker for certain things, but a gaming GPU and a cluster GPU are not really comparable because of what Simo just said.
Yeah, but the question is that what is the calculation? What do you want to do? So, for example, if you want to learn how to do GPU programming, like it doesn't matter how bad the card is as long as you can run the CUDA code on it, right? Like if you want to train on the stuff, like you can use like the crappiest GPU card as long as you can compile to that GPU card. And similarly, if you have like a gaming GPU and if you want to see that, okay, did I write my code correctly? It's right here. It's right in my machine. I can test out like, does my model start? It can be really slow, but I can see that it starts. If it starts, I can then make it, put it into the cluster and put it in the queue. So what Richard showed, like the queue can be really full. And if you're developing something, you don't want to be waiting there. So then, like we usually recommend that people who are actively developing like deep learning stuff, if the stuff is something that they can run on their own machines or on a workstation, they get a workstation with a GPU. Even if it's a crappy GPU, you can still use it because it's there. It's for you. It's always allocated for you. But we cannot allocate these like GPUs that cost thousands of euros for everybody because there's no money. So in those cases, like those, it's better to use those really high power GPUs for really these tasks that require really high power.
This is also a bit of the reason why we sometimes check a bit on the efficiency of general jobs and might contact people if we see that, well, you're requesting for GPUs and they are idling.
Yeah. So there's still not a lot of votes in the feedback. Please, if you're hearing this, feedback, whether it's good or bad, is what keeps us going here. So about the feedback, there's comments on like it's too fast and we didn't go deep enough and things like that. Yeah, that just sort of how it is, basically. So
that's the problem of a
what we're
Kickstart.
teaching here,
You're
yeah,
getting an
this could be
overview.
a multi-week course.
Yeah.
But if it's a multi-week course, then people wouldn't have time to actually come to it. So yeah, what do we do?
Yeah, what we mentioned previously, that like you don't have to like remember everything. Like it's like it requires that you encounter the same thing multiple times until you form a pattern to recognize it. But like hopefully this course helped you in some way to recognize certain patterns so that you can then, if you encounter them in the wild, you can then apply them to your work. So like now you know that, like for example, shared memory means this kind of a thing, or CUDA means this kind of a thing, or something like that, hopefully.
Yeah. Should we look at the feedback some more? Well, there's the question, what does it mean? What does crashing of such big GPUs mean? Did you just answer that?
I was just typing and asking what was meant with crashing. I think the most common thing besides programming mistakes that we see is not having enough memory on the GPU card. That happens with some large models. Other than that, there's the very, very rare strange error that is sometimes not even reproducible. But
I mentioned here that like for example, like what I mentioned about the double precision not being present in the gaming GPUs, like usually to save memory and to create bigger models and to have more training data on the GPU memory, people in deep learning usually have utilize like lower, like they utilize like shorter numbers, because that even like having a shorter number also makes it so that the model doesn't like overfit. So like if it doesn't have the parameters to overfit, it cannot overfit. So and then you can have more of these numbers in the memory. So many of the gaming GPUs are still good for deep learning, for example, because you can use these single precision numbers, and of like this might happen, like these crashes might happen if you have like if you try to use the full double precision numbers and have a big model that you're trying to run.
Okay. Oh, it is now the hour, so I guess we are out of time. Any comments or feedback? What is support for CSC on Zoom? Maybe we can take this to them and ask for someone to come in future years. But yeah, I mean, there's too much stuff. We understand you're tired. That's why there's videos, and this is more a starting point than an ending point. And we're really happy for people to come by to give individual support for the things that you in particular need. And I think that's our strategy now.
it's also a bit giving you an overview what is possible, so that you even that you can start with, okay, these are the things I can do.
And also I mentioned that if like you in the future, if you encounter like a nice problem that would fit as an exercise, I'm really happy to take them over. Like because like the hardest part of these courses is to give exercises, like meaningful exercises, because like you notice the pi exercise, that's not really like that's something you run in the wild, right?
Yeah.
But it's very hard to give an exercise that both demonstrates what the queue tries to think and also what the code tries to think. This course is much more directed towards like what the queue thinks and how do you be like work in the cluster environment and that sort of thing. So it's very hard to get into the nitty-gritty of what the code should do, like how you should program your code and that sort of things. But maybe we should have a like there were questions about GPU computing. Maybe we should have like a course on these things, but it's very hard to create if you don't have good examples that you can use as this kind of like, okay, like let's start coding on this starting point. So if you encounter that on the wild, let us know. That would be interesting.
Maybe we could have
and also I was going to say an intrinsic problem with better exercises is that if there is any exercise that took more than a minute, then it starts taking so long to run them that exercises becomes a really long time. And anything that's advanced enough to be real, then there's so many other things that people need to know in order to just do them, like a lot more of the shell stuff or data management, whatever. But anyway, Tim, what were you saying?
Yeah, I was thinking that maybe one thing that a lot of people use is the scikit-learn Python library. And there you have the njobs. And people might be even already kind of familiar with it. because you have on your own laptop, you have a couple of CPUs. So if you use like 4 n jobs, then it will parallelize to 4 CPUs. And then if we make some example using that, and then run it on the cluster using, for example, 20 CPUs.
Yeah, maybe we should just like maybe we should just like, I don't know, like have some sort of like a example software package that people could download and then run, because like the problem is that like if we want to make this general, then other clusters might not have the software available, and like it's, I don't know if I want to make like a install conda environment at the start of the course, because that's,
I mean, we've basically done this with what's it called? With the Pi example. So it's like a little project. Yeah, let's go. So the Pi example, even though it's really trivial, is sort of how many of us would do this. We have the code in a Git repository. It's been developed on our computers. We go to the cluster, we pull it there, and we can run it. First, we can run it with just a few CPUs for testing. We can slowly add in more CPUs for advanced things.
Yeah, maybe we should like have it done like that. Like maybe we should have like this kind of like, okay, let's move this code to a cluster, and like have this kind of like workflow, kind of like a story behind the whole thing.
Because
kind of like
line
that we move.
Because actually, it was the workflow that I think majority of us use, but we just skipped the very beginning, which is that you develop it on your own computer. Yeah.
Okay, now we're 5 minutes over. Should we keep talking or wrap up? Are we all tired?
But
I need the ice cream that I spoke at the morning.
Yes. Okay. Well, maybe we'll let everyone go, not that you had to stay anyway. So thanks for sticking it out to the very end. And come back and ask us for more help next week. Okay.
Yep.
Thanks a lot.
Thanks.
Thanks a lot.
Bye.
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 We'll miss you.